Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Conic Sections, Rotations of Axes. As always, please be an attentive learner while watching this video. By way of introduction, previously in this course we studied equations of the form this, where the major axes of the conic section was parallel either to the x or y axis. Clearly this isn't always the case. So in this section we generalize this and show that the general second degree equation, which looks like this, can be analyzed by rotating the axis so as to eliminate the term bxy. This term is especially nasty when you're trying to do analysis because you can't complete the square effectively with this. So here's what we're going to do. We're going to take a conic section and we're going to rotate the axes. And so the x-axis will be rotated at an angle of theta. And this will be a rotation that we're doing in the counterclockwise direction. So what will happen is the black x and y axis become red axes, and one of them is called capital X and the other one is called capital Y. And now if we look at these and we're comparing the results before and after rotation, you can see from this figure that x, capital X, is equal to r cosine phi. Now phi is this angle that you're making there, so that's with respect to the capital axis, and phi also the angle that this point is making with respect to the capital F axis yields that y is equal to r sine phi. So there's capital Y and here's capital X. But here we're x and y. But then when we drop the perpendicular, notice it's the same point. It is lowercase xy or it is uppercase xy, but it's the same point. It's just we're changing the axes from lowercase to uppercase. So we get this, and what we can see then is that x, which is this point, is going to be r, which is the distance there, but the angle now is going to be theta plus phi. So x is r cosine theta plus phi, and y is equal to r sine theta plus phi. Now I want you to realize that if we take a conic section, we just rotate it about the polar axis, about the point 0, 0. The form of the conic section is preserved under rotation. That means that an ellipse will go to an ellipse, a circle will go to a circle, a parabola will go to a parabola, and a hyperbola will go to a hyperbola. Okay, so what we're doing again is we're trying to see, is there a way that we can rotate this to eliminate the term bxy to make it look similar to this so we can do analysis with it. Okay, so this is the setup. We have these equations. So continuing then, what we will find is, and we're substituting into those equations that we have, so x was equal to r cosine theta plus phi, but we have a trig identity for cosine of theta plus phi. We studied this when we were doing the integration techniques in chapter 8. So I just expand that, the r sits there, and this is the trig identity that I expanded. And then I distribute the r and do some associative properties, so I will have r cosine phi, cosine theta, minus r sine phi, sine theta. But this is the same thing as capital X, and this is the same thing as capital Y. So what we have is, we have that x is equal to capital X cosine theta minus capital Y sine theta. That's what we have down here. And a similar calculation for y. So we would do y is equal to r, and it will be sine, and the equation is different, but whenever you do it, and I encourage you to do the calculation, you'll get that y in the original coordinate system is equal to capital X sine theta plus capital Y cosine theta. Now what happens is, these are two equations and two unknowns. So I can solve these for capital X and capital Y. So I have, this is what capital X is, and this is what capital Y is after I solve these two equations and two unknowns for x and y. Notice that we're calling this equation 2 and this equation 3. Let's take this transformation out for a little bit of a ride with an example. This is example 1, and again, I encourage you to actually try to do this example, and we'll see how you did. Certainly, if some students have asked, how can I prepare better for test? I'll tell them go back and redo these problems. You have the answers here to see if you get them right. But anyway, okay, so we're going to use equation 3, and equation 3 is written down here for your reference. But now x is 2, so I put 2 there. And y is 6, so I put 6 for the y, and theta is 60 degrees in this problem where we're rotating through 60 degrees. We want to find the x, y, capital X, capital Y coordinates of the point whose xy coordinates are 2 and 6. So we're going to use this equation, and we find that x is equal to, we substitute in, this is 2 times a half plus 3 times square root of 3 over 2. That gives this for the capital X coordinate. And the capital Y coordinate is going to be, I'm substituting here into this equation, and this will be minus 2 times the square root of 3 over 2. And this is going to be, the cosine of 60 again is a half, so this is 3 minus the square root of 3. So the xy coordinates are 1 plus 3 root 3, comma, 3 minus 3 root 3. Again, I'm usually going to be looking for the exact answers. Now we're going to move on, though, and now we're going to try to determine the angle theta that will eliminate the bxy term in equation 1. And this was equation 1, and you see you do have this difficult to deal with bxy term. So we're kind of try to see, well, can we pick theta to eliminate this? So what we're going to do is we're going to substitute equation 2. This is equation 2 that says what x and what y are. So we substitute that into equation 1, and this is equation 1. So when we do that, we straightforward substitute this, and this into the equation. Now what we're going to do is we're going to expand and collect terms, and now what we get is we will get a prime times capital X squared. And I encourage you to do this algebra, and b prime times capital XY, c prime times y squared, d prime times capital X, e prime times y, plus f equal to 0. And you could call this an f prime, but it's going to be the same constants. And in fact, if you were to do that, this is what you have for a prime, c prime, d prime, e prime, and f prime. And I encourage you to do these calculations to make sure you understand what's going on. But well, the coefficient of b prime is going to be this. So the coefficient of b prime will be 2 times c minus a sine theta cosine theta plus b cosine squared theta minus sine squared theta. Now this is a trig identity, so that is cosine of 2 theta. And this 2 times sine theta cosine theta is sine 2 theta. So here is b prime. We want b prime to be 0. And so we're going to figure out what does the angle have to be. So I'm going to call this c minus a times now sine of 2 theta plus this is b times cosine of 2 theta. And I'm setting this equal to 0. So I put 0 there and I solve for this. So I put 0 here and I'm solving for theta. And so I will get this is equal to 0. Actually this is equal to 0 when I move this to the other side, and then I will divide all the way through by the sine of 2 theta, and that gives me a cotangent of 2 theta. And so you see the cotangent of 2 theta has to be a minus c over b. We're just solving this equation. So that tells us what the angle is that will make b prime equal to 0. So we've eliminated that b in the equation. That was a lot of work, and that actually was a theorem. So if I start with this and I transform it into this, by rotating cosine 2 theta a minus c over b, what will happen is I've eliminated the b, so I get it into this, and notice there is no b prime up here. And these are the coefficients I used, and these are the calculations. So that is a theorem that we have just proven. Another problem that you really should try to do. Show that the equation of xy equal 1, that's an equal 1, is a hyperbola. Now xy equal 1 is going to look like this and this in the black xy axes. But we're trying to rotate it and show that this is a hyperbola. Okay, now this is the form of equation 1. And you see a is 0, b is 1, and c is 0. Here's equation 1. Okay, so b is 1, and the rest of those are 0. So according to the equation that we proved in our theorem, the xy term will be eliminated if we choose theta so that the cosine of 2 theta is a minus c over b. Now a is 0 and c is 0, so that is 0. So we're trying to choose an angle such that the cotangent of 2 theta is equal to 0. Well, that's true if 2 theta is equal to pi over 2. And that means theta is pi over 4. So that means we're rotating this through a 45-degree angle or a pi over 4 angle to get these. So then what are the sine and cosine for those? Well, the sine of pi over 4 and the cosine of pi over 4 are both 1 over the square root of 2. So x becomes capital X over square root of 2 minus y over square root of 2. And y becomes capital X over square root of 2 plus y over the square root of 2. So we substitute those expressions into the original equation, which is up here. So we take x times y equal 1, and we simplify. We're doing some algebra, but when we simplify that, actually you're taking something minus the first thing minus the second, and this is the first thing plus the second. So this is going to be capital X squared over 2 minus capital Y squared over 2 equal 1. That is a hyperbola, and that's a hyperbola that is now represented relative to the red capital X and capital Y axes. So this is a hyperbola. The vertices in the capital X, capital Y coordinate system are plus or minus root 2, 0. And the asymptotes, again in that section, are y equal plus or minus x in the capital X, capital Y system. And we could change that back into the xy system also by using our other conversion. You see, this is really a powerful technique to do analysis on this conic section. Here's another example. Identify and sketch the curve that looks like this. Now this is 73x squared plus 72xy plus 52y squared plus 30x minus 40y minus 75 equal to 0. And again, what we'd like to do is get rid of this xy term. So, and again, we talked about equation 1. That's the one we always have, and this is the general equation 1. But a is 73, b is 72, and c is that. So the cosine of 2 theta, that's the angle we want, is going to be a minus c. Now a minus c here is going to be 21, but I'm putting it in lowest terms. It will be 7, and b is going to be 72. So what we get is 21 over 72, and in lowest terms, that is going to be 7 over 24. But that means the cotangent of 2 theta is 7 over 24. Again, we can draw a right triangle. So here is the 2 theta angle, and the cosine of 2 theta then, that's the adjacent over the hypotenuse, is 7 over 25. We can use the Pythagorean theorem to figure out what this is. This is going to be 625 minus 49. That's going to be 576, the square root of that, and so that is 24. So this is the right triangle. So now we know all our trig functions. So the values of cosine theta and sine theta for our transformation can be computed from the half angle formulas. So the cosine of theta is equal to the square root of 1 plus 2 cosine theta over 2. So I substitute that in, I do the calculation. I get the cosine theta is 4 over 5, and the sine theta, doing a similar calculation, it's a different half angle formula, is going to be 3 over 5. Check these calculations to make sure you understand what is going on. But now we have to continue with the problem. So the rotation equations then is lowercase x is this, and lowercase y is this. So we're going to substitute that into the equation we had at the beginning of the problem for x and y. So we substitute in, and we do the calculation. and we simplify. There's quite a bit of algebra involved in the simplification, so you should do it. But what you will get when you simplify is 4 capital X squared plus y squared minus 2y plus 3. And this is an ellipse, but what we're going to do is we're going to complete the square. And so this will be 4x squared plus y minus 1 whole squared is equal to 4. We divide all the way by 4. And we get this is x squared plus y minus 1 whole squared over 4 is equal to 1. Well, this is an ellipse, and in fact we can graph that ellipse, but we're graphing it in the capital X, capital Y format. And so we can look at this, and this is an ellipse. You can see what it is. That tells you what the angle is approximately, and I probably would want you just to tell me that is the inverse cosine of 4 over 5. It's close to that, and there's the graph. And you see this is rotated, and so that's what we see. Now, if we wanted to, but we now are able to graph it, and that is what it looks like, and it's the same graph, whether you're graphing it in the X, Y, capitals or the red or the black. So you see this set of points, the blue is either this or this, but now we were able to easily graph it. Here's another example, and again you should really try to do these examples. Sketch the graph of 7x squared minus 6 square root of 3xy. Again, you see you've got a term that you really don't like so much, plus 13y squared minus 16. Okay, we know we're seeking an angle that is cotangent of 2 theta is capital A minus C over B. So we do that calculation here, and we get that the cotangent of 2 theta is 1 over the square root of 3. Now we draw a triangle, and we think through this, and you should do this, but that will tell us that theta is equal to pi over 6. Okay, so pi over 6, we know that the cosine of pi over 6 is root 3 over 2. The sine of pi over 6 is a half. We substitute that into these equations, and after, and it says here considerable algebra, I encourage you to do that. What we have is this is in the transformed system, which is shown dotted here. And so this is the equation in standard form, and we see that this is an ellipse centered at the origin with vertices at plus or minus 2, 0, and that is in the rotated dotted coordinate system. Here's another example for you to practice. Here we're rotating the axis for a parabola, except you don't know it is a parabola yet, but you're sketching the graph of this. We want to make this xy term equal to 0. So we're going to rotate to an angle that is cotangent of 2 theta is equal to 3/4. Make sure you see where these numbers are coming from. And then we're going to use this trig identity because we know the cotangent of 2 theta is 3 over 4, but we're going to use this half angle formula. The cotangent of 2 theta is equal to cotangent squared minus 1 over 2 cotangent theta. So that means that 3 over 4, which we have up here, is equal to this. The only thing we don't know is the cotangent squared of theta. So we're going to solve this equation. 3/4 equal this. And so we work through that. We get it equal to 0, and we can factor this into this. Now here, the cotangent is, if I set this one equal to 0, the cotangent is negative, which means it's not in the first quadrant. But we're assuming it is in the first quadrant. That's what the kind of rotation we're doing. So it follows that the other one is equal to 0. So the 2 cotangent of theta is 4. That means the cotangent of theta is 2. And also, then we can draw the triangle. If the cotangent of theta is 2, that means it's 2 over 1. So we can do a calculation to figure out this is the square root of 5. So we know that the sine of theta is 1 over the square root of 5, and the cosine of theta is 2 over the square root of 5. We substitute those in our equation for x and y to get these relationships after we simplify. And then we're going to substitute these values into our original equation. And here we do that, and we simplify. There's quite a bit of algebra here, and we will get this, and then we will complete the square on the y prime here, and we'll get this in standard form, looking like this. And that is a parabola. Its vertex in the x prime, y prime system is 4 over 5 minus 1, and anyway, here's the picture. and that angle is about that after you rotate it. So here's the set of points that you have. And again, you can give me values that are in the rotated system or the other system in the XY. And all you need to do is do these equations that we've spoken about. Okay, as we said before, the form of the conic section is clearly preserved under rotation about a pole. And there are other things that are preserved, and if we look at this set of equations, the proof of this follows from explicit calculation. You can just look here. If I add a prime plus c prime, and remember that the cosine squared of theta plus the sine squared of theta is equal to 1, I know that a prime plus c prime is the same as a plus c. And also f is the same thing as f prime, and b prime is 0, so b squared minus 4ac, you can look at the calculation over here and verify again by explicit calculation that b squared minus 4ac, which we used to call the discriminant, is also invariant. So the form and these are invariant when we do it. But since the form is preserved, that tells me that I can understand what this is, and I can use this to help me determine what kind of a conic section it is. And here's this theorem. And the proof is straightforward. Here's the thing we're transforming, and this b, after you do it, is going to be 0. So that means that it might as well be 0 here. And so if the a and c are of the same sign, that means this is an ellipse or a circle, because this will be less than 0. If a times c is equal to 0, then it's a parabola, because one of them is 0, not both. And if a hyperbola, one is negative and one is positive, which means this is greater than 0. So this theorem says that that graph, we have a test that is determined by the discriminant b squared minus 4ac. If b squared minus 4ac is negative, it is an ellipse or a circle. If b squared minus 4ac is equal to 0, it is a hyperbola. And if b squared minus 4ac is equal to 0, it's a parabola. And if b squared minus 4ac is greater than 0, it is a hyperbola. Again, you should test this problem, but using the discriminant, we can determine what are these equations. So here, this one is a. B squared minus 4ac is 16. That's greater than 0. That tells us it's a hyperbola. B is this one. B squared minus 4ac is, let's see, that would be negative 7, is less than 0. So that's an ellipse or a circle. And in fact, if I look at it, let me look at it again. It was a B. That is a circle, as it turns out, because those coefficients are the same. And this graph is a parabola. That was C, because b squared minus 4ac here is 0. That makes that a parabola. And the last one, which was up here, is a hyperbola, because if you compute b squared minus 4ac, you get 16, which is greater than 0. Kind of cool, huh? And this is a very easy question for me to ask on an exam. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.